Okay, so I think we can start. It's 3 p.m. UK time. Welcome everyone. Thank you for joining us today. I'm happy to introduce today's webinar on exploring new computational frontiers with the SmartSim. Now let's get started. I'm delighted to introduce today's speakers, Alessandro, Andrew, and Holly from HPE, and Andrew Moll from Imperial College London, who will introduce SmartSim. So floor is yours. Thanks.
Yeah, so I'll say a few words. So I'm Harvey Richardson. I work in the ARCHER2 Center of Excellence. And so we know that this topic's an interesting one to various people as it's bubbled up in a few conversations. So the idea this afternoon is that we'll have a presentation, as you can see the title on the screen, from Andrew Shao of HPE. And then that'll be for around about 40 minutes. And then Holly Judge will give a quick recap of her experience in trying to use one of the SmartSim examples on ARCHER2. So you'll get a feel for how hard would this be if you wanted to try it. And then Andrew Moll, who's involved from Imperial College, who's involved in a project which has been using SmartSim on ARCHER2, will say something about what he's doing. So there might be some overlap between the three components, but maybe from some slightly different perspectives. So hopefully we can all get different perspectives on things and learn something. So I'll hand over to Andrew now. Well, we have two Andrews. So Andrew Shao.
Yeah, I'm Andrew the first. I'll go first. Let me just make sure I get this up. Thanks for that introduction, Harvey. And yeah, I got teed up to do some of the general introduction for this. So hopefully, yeah, like I said, whatever I cover here will be fairly shallow, including some of the work that I know that Holly wants to demonstrate too. So hopefully, yeah, repetition won't be the name of the game for the entirety of the session. Yeah, so thanks everyone for taking the time out of your days to come and listen to us talk about a project that I've been working on along with Alessandro for, I don't even know at this point, maybe three or 4 years. I just want to give a background to myself for those who don't know me. My background is actually in climate science. I have a PhD in oceanography from the University of Washington, and then I contributed to CMIP6 for the GFDL model, and also worked a little bit with the NCAR folks, and then really did a lot of stuff for the Canadian Center for Climate Modeling and Analysis, which was my previous position before I joined HPE. Yeah, so just want to kind of give a brief overview about why we think that SmartSim is a good project to work on, and also primarily the thing that Alessandro and I really appreciate about it is the fact that we get to play around with both AI techniques, but then also traditional computational simulation kind of things at HPC scales. So this is a question that we get a lot, actually, both externally and also internally within HPE, right? So there's a lot of new uses of AI that are kind of are creeping on the domain of what we kind of traditionally think of that scientific simulation does, right? And so one of the big movements of this has been the use of surrogate models, like full surrogate models, to do things like weather, right? And I know a lot of folks who are in ARCHER2 are affiliated with NOC, the UK Met Office, obviously ECMWF2, and ECMWF in particular, right, has been actually operationalizing ML-based simulation for doing their short and medium-term weather forecasting. And so there's this very natural question of, okay, well, does AI replace our traditional HPC simulation? And the answer is really no, right? And I think if you ask anybody who's actually doing the training of these models, building these surrogate models, I mean, what they'll tell you, right, is at the end of the day, all these things are being trained on simulation data, right? They're trained on the error reanalysis that the ECMW puts out, or various other reanalysis products, mainly for the reason that a lot of science uses simulation, right? That we just don't have enough observational data to actually train these surrogate models to learn the physical systems themselves. So yes, the answer is AI replacing numerical-based approaches, no. There will always still be limited by data. There's a lot of benefits from doing this, and we definitely do not want to discount the advantages of having these surrogate models there, right? They can be run much more quickly. You don't need all this infrastructure like you might need to do to run the forecasting systems. There's no compilation steps. you just feed it some inputs and you get the outputs out of it. And of course, all these machine learning packages and the infrastructure around them have been making it very easy for someone to just download a model, spin it up, and start using it. One of the downsides, though, especially when we think about it and approaching it from a scientific lens, is that there are a lot of downsides to these AI models, right? Unlike a scientific simulation, where if you can write down a new differential equation or some new representation of some process and simply add it to the model, there's no real equivalent of doing that when you're training an AI model, right? Because like an AI model is not driven from first principles. It's not necessarily solving a differential equation. And so the question of how do you add complexity to that model? Well, the only real answer is you have to give it new data, right? So that's one downside of the AI model, right? It's very good at replicating things that are already there, but not necessarily generating new data with unseen processes, unresolved processes. And then, of course, a big one, and when you're thinking about this in terms of a climate context or a physical system that may experience extremes that go outside of its training data, is how well do these AI models extrapolate, right? So like every other kind of predictive model out there, whether it's statistical or AI, right, extrapolation becomes a really big question. So one of the things instead that that we want to say, okay, can we take the best of both worlds, right? Can we have this harmonious balance between HPC simulation instead of this question of should we replace AI with HPC? We're kind of thinking about a lot of different computational paradigms, a lot of workflows that kind of involve the wedding of these two somewhat disparate disciplines, and figure out, okay, where can ML be useful in the context of AI? And then also that reverse question, where can simulation be useful in the context of AI? And so as we've kind of talked with a lot of our collaborators and all our users, we've kind of realized that we kind of need a taxonomy to talk about how we're combining AI and ML with scientific simulation. And one of the really useful places when we talk about it in the abstract across disciplines, across domains, is where is this ML being coupled to the simulation, right? Or even is it being coupled to the simulation? And so we've kind of come up with this language about, okay, where is this ML placed in the consideration of the inner loop of the simulation? So what we call ML in the loop is when these machine learning predictions and or training is done at nearly the time step level, right? So like every single time step of the simulation, you might want to use a machine learning model to predict a term on the right-hand side of the equation, right? Maybe it's a forcing term, maybe it's something trying to resolve, to predict the consequences of unresolved physics. Maybe it's doing something where you really want to train a high-frequency data coming from the simulation, but something that's interacting with ML at that time step level, right? Like highly, highly coupled at the time step level. This can also be things like maybe you want to just see what the simulation is doing and check in on the state of the simulation. Maybe you want to apply some kind of on-the-fly analysis for a streaming algorithm, while the simulation is running. And we have examples of that, which we'll talk about. And then we also have this concept of ML around the loop, right? So this is applying a type of ML method or AI model around the simulation. So it modifies inputs, it monitors outputs, and then it's doing something using that information from the simulation and the way that it modifies this. So two kind of exemplar cases are doing something like parameter tuning, right? So a lot of our simulations have tunable parameters, which we have some known constraints on, but maybe for your specific case, you don't know what the ideal set of parameter values is for your particular simulation based on some figure of merit. So you want to do some kind of automatic parameter tuning. You don't want to go and tune by hand. Reinforcement learning, which I'll talk about also, is a very natural case of this as well, right? So we can't necessarily prototype and create a physical prototype of something and see how it interacts in a physical system, in a lab setting, in a production setting. But we want to use a simulation of that environment to test some of these like control problems, methods of figuring out like, okay, like how do we get the behavior we want from a physical system? How do we control that system? And so just to want to keep in mind these two things, right? There's obviously some gray areas in between these things where like ML on the loop, maybe there's something that needs to be done, not necessarily at the time step level, but maybe it needs to be done like some large number of time steps, right? Maybe it's not at the time step level, maybe it's like every 1,000 or 10,000 time steps. And then there's also like edge AI, right? Which we won't talk about today, but this is this concept of like federated workflows where you have both physical systems needing to interact with the supercomputer. How do you do that? How do you do those simulations on demand? How do you transfer the data? And that's a really, really interesting field of research, but not one that we'll concentrate on today. So these two paradigms, ML in the loop and ML around the loop, are what we're going to really focus on today. So really, this all is coming into play where we have a new scientific paradigm that people are working on, right? Traditionally, a lot of the times we have used simulation where the simulation and the output of a single simulation or set of simulations is actually the scientific output, right? From which we generate the data. We set up a simulation, we run the simulation, and then we simply analyze the output and we write our papers, and we get a lot of really good scientific insight into processes by doing that. This can all be kind of described like a pipeline, right? Because it's just, here's a stage, here's a stage, here's a stage. And there's not, you might have a horizontal scaling where you're running large ensembles of these things. Maybe you're exploring a parameter space, but really like each and every one of those things is independent. In the new context where we're thinking about combining AI and ML, what we've also realized is that there's actually a much more complicated paradigm of computation that's necessary than what can be traditionally described by a pipeline. And so we kind of think of this where, okay, the simulation itself is just but one component of an entire sequence of, or entire set of interacting components, right? So there might be things where the simulation is providing data to 3 or 4 other different things that might be running. So for example, you want to train a surrogate model for some physical process while the simulation is running. Maybe you want to do some of these things like visualization analysis. Maybe it's calling out to doing some kind of ML model prediction, but this is all happening interconnected while things are all simultaneously running. Some of them may be running synchronously, where they're depending on the inputs and outputs of some other aspect of the workflow. And maybe they're done asynchronously, where it's just providing something and just waiting for things to happen, but they're not that tightly coupled. So a lot of the things that are involved in these kind of things have branching statements in them, or like, only do this if this is available, or something like, okay, now this is ready. And this is very, very challenging to describe in traditional pipelines. So one of the things that we have noticed that we've come to realize as we are entering this phase where we have a bunch of things interacting with each other, that there's a couple of fundamental challenges that need to be addressed. So one of them is that we don't really want to very tightly couple each of these applications to each other, right? We don't want to do things like join the MPI COM worlds for 100 different applications or even 5 different applications. That gets very challenging. There's limitations to the underlying communication paradigms that MPI requires. And so really, we need something else. And so one of the things that we provide for SmartSim is a central location to share all the data that may be generated or consumed by the elements of the workflow. And then the second challenge that we have is that we have come to realize is that we need to provide a way for domain scientists to actually define the workflow and execute complex experiments, right? Like this is not something that can necessarily be done very easily with just like bash scripting or like anything that's really like pipeline oriented type workflow managers. Oops. Yeah, so for example, just to really kind of hit home some of these things, like all these things, which I'm not going to read out one by one, but all these things could be happening all at once within the same application. And this is really what we mean by the convergence of HPC and AI, right? That there is now not just a single set of tasks that need to be done in sequence. There's really at every single step of the entirety of the workflow, there may be multiple things that are happening that all contribute to the execution of the final workflow, which now is not just the simulation as the final output, but the entirety of the workflow as it. And so in today's talk, we'll kind of give some examples of this, of two or three of these things interacting all together to kind of inspire you, hopefully, to figure out, oh, maybe there is room for me in my scientific investigation to start thinking about some of these more complex workflow paradigms. So SmartSim, the project that Alessandro and I are lead developers on, it's an open source library, and it tries to tackle this problem directly, right? Like, how do we actually converge HPC and AI? And really what we started as was that we were seeing all these data-driven techniques kind of like becoming really, really popular, and there's been a lot of money being put into them, and the accessibility for like a graduate student just be able to pick up this really powerful toolkit and do things like train a model to predict subgrid scale turbulence or something like that. There were many papers that were being done, and so the natural question was, okay, well, how can we take advantage of this inside of our simulation? So that's really where SmartSim started from, right? Is that we really wanted to figure out a way to make this easy and seamless for people. And so very early on, we settled on this idea of loosely coupling all these components. And by that, I mean that they aren't joined together, like the communications are not joined together, but instead, it's a really data-driven approach, right? A data availability-driven approach where a simulation might just send data, and then another part of the workflow will notice that there's new data for it to consume. And so that's like I said, that's a new paradigm, I think, for a lot of scientific computing. And so one that is does not have a lot of tooling, but we, as part of SmartSim, we try to provide that. So again, one of the things that we are really trying to do for this is to simplify things for the users so that they can do things like call ML inference, exchange data between applications that workflow components are written in C++, Fortran, Python, so like cross languages. You might want to do the analysis of things, you might want to train things. And so how do we actually accomplish this without touching the file system, right? So that's the other bottleneck that we saw, was that a lot of times people just kind of use the like Lustre or a file system as scratch space or swap space to do some of this handling of like handoff of data back and forth. And of course, that makes HPC administrators unhappy. File systems are also just relatively slow compared to keeping everything in memory. And so to alleviate that bottleneck, this is where we really kind of came on this fundamental idea that's diagrammed on the bottom here. And so what this is showing is that we have essentially at the very center of this, something that we call a feature store. So this, if you want to think about it, it is very well represented like a database that can hold AI models. It can hold arrays of data, like numerical data. It can hold code and scripts, and you can also execute some of these things too, right? So it's not just a database, but it's actually a computational engine of some variety as well. And so if you have an application, then the question is, how do you actually send data to this database, right? Because we don't necessarily have things like SQL like calls within a Fortran application, right? So what we provide is something that we call the Smart Redis client. And so essentially what that is, it's a very lightweight communication library that you link into your application in very much the same way you would do like NetCDF or XiOS or anything like that. And you just link it as part of the application, and you instrument your Fortran code or C++ code with just a couple of calls, and that allows you to interact with this database and send and receive information and do some commands for the orchestrator. And so what does the first day experience look like? So again, like, this won't go too terribly much into it, but on the left-hand side here is a very simple just hello world. And so one of the things that we knew that people were doing, right, is that we're operating our HPC applications on HPC platforms. So, and sometimes, you're on one machine that has Slurm, you might have a different scheduler on a different machine, but you want to be able to port these things back and forth. So one of the things that we do and recognize as a useful thing for people is so that we can write this driver script and make it fairly independent of like platform specific things. So on the left-hand side is a very simple just hello world. This is the easiest, like the smallest experiment that you could run on a supercomputer that uses SmartSim. And it does things like create allow you to create represent elements of your workflow. So, for example, your simulation. Maybe there's a training task, maybe there's ensembles of simulations, and so it's all described in a Python driver script, right, which describes the execution of this workflow, which can have loops, which can have branching, which can monitor state. You can all do all these things. And then the second part of it is that you add those smart Redis lines to your simulation code, and then you execute the entirety of it, and things will hopefully just work. Obviously, you have to, there's always development involved, so you have to go back and forth, but we have discrete ways of developing. And really, what we find is that people do, once they kind of understand how to do this kind of data-based approach, it becomes very simple for them to imagine how to create these very complex workflows. Okay, so now we're going to go on to some scientific applications. Really, like, those slides that we were just introducing were just generically like, okay, these are the kinds of things we want to do, but now we're going to really dive into some specific use cases that we worked on with our collaborators to demonstrate the utility and the promise of converging HPC and AI methods. So again, we're going to focus first on ML in the loop. So this is where we're doing inference or training every single time step of the simulation. So the very first example of this that we created was this question applied to the question of ocean modeling. And this was mainly because I worked on the development of ocean models, both MOM6 and NEMO, and I knew it really well. And I knew a lot of the problems that we could do. So like most fluid systems, the ocean has turbulence. And one of the really challenging things for ocean modeling is how do you resolve the effects of the turbulence without actually resolving the turbulence itself, right? So there's some subgrid scale process that's happening that does affect the entirety of that is a first order effect on the physical system itself. And so there are actually two different problems that happen in oceanography, right? So there's one, how much eddy kinetic energy actually is there when you don't resolve it? And then the second part of it is like, what can you do with that, right? Like, if you know what's happening there, if you know what might be happening at subgrid scale level, how can you inject that information or like those processes into the simulation? So one problem is this question of eddy kinetic energy. The second one is that we know that our models are very diffusive. The eddy viscosities and these things are very high. So how can you re-inject momentum into it in a sensible way? So in both these types of problems, right, like how do you come up with these things? And ML is a really good approach because there are no closed form parameters. There is no closed form solution to this, right? We have approximations of this that we've been able to make a lot of good progress in oceanography and fluid dynamics to resolve the effects or to capture the effects of turbulence, but they're incomplete, right? It's very challenging to take Navier-Stokes and bottle it down to something that really solves the question of turbulence. But we know that there are relationships, right? If we take a look at high resolution simulations, large eddy simulations, direct numerical simulations, we know that there is some relationship that you can just kind of visually see between the turbulence and the resolved fields. And so we think that we might not be able to describe it in a single equation, but maybe a data-driven approach using ML is actually successful. And so this is essentially what we did. We ran high-resolution simulations that resolved the turbulence, and then we trained an ML model to estimate the eddy kinetic energy. We trained an ML model to figure out how to add the energy back into the system to the mean scale resolve flows, and then we wanted to embed the prediction in the simulation. So the way that we do this is that we have an ensemble of MOM6 simulations on the left-hand side. Each of these have the Fortran version of our Smart Redis client embedded in them. Each of them are calculating features that are used to do the ML prediction for each of these things, and they're being sent to the database. And so that's what's represented on the right-hand side. There's this in-memory feature store, which can accept the data, and it's storing the pre-trained versions or the pre-trained models that will predict EKE and these extra momentum terms. And one of the things that you can see on the right-hand side too is that this database can actually be distributed, right? So it can be scaled to match the load of the system itself. So that's what that shard 1, shard 2, shard 16 is. That's essentially saying that we have 16 nodes that are all behaving as one database that can handle the communication and the running in the machine learning model. So what happens in this ML in the loop loop? Mom6 sends features from the database. Mom6 will then send a command to run the machine learning model in the database based on the inputs, and then it will ask for the inference results back. So there's a couple of things to note here, is that there's only two places where data gets moved, right? There's the sending of the data from the simulation, and there's the retrieval of the data from the database and then incorporated into Mom6. And the other thing that's really important to note here is that the database is the thing that's actually running the ML model inference, right? And so that's the only thing that actually requires a GPU. We don't require a GPU on the simulation side of it. And this has a lot of advantages for when you have systems that might have limited amounts of GPUs. A lot of the other things out there solutions out there that try to allow you to call ML models from inside the simulation require that there's a GPU on every single node that the simulation is being run on. Whereas here, really, there's only a small subset of the processes of the nodes that need it, which are dedicated to the orchestrator. So for example, on the left-hand side, when we ran this thing, we used something like 150 nodes on a supercomputer to run the ensemble, and those were all CPU-only nodes, and then we had 16 nodes that were just dedicated with GPUs on them. So that's a factor of like 10 that we allow for in terms of like more efficient use of GPUs, right? Since it's not that we have 150 nodes of GPUs on them, we only need 16. And so won't belabor this too terribly much, but we did also, I mean, the question is, does this actually do anything? Does it do anything reasonable? And the answer is yes. We got much better results using the ML-based approach than the traditional PDE-based approach for calculating eddy kinetic energy. On the right-hand side is an animation where we had this other model that was injecting momentum into it, and it kept the simulation stable. It did energize the flow quite a lot. If you do see a comparison between two of these things, there's much more turbulence and energy in the right hand when we added this backscatter or this energy injection routine into the model itself. And of course, one of the big things is also asking the question of, okay, well, does this incur computational cost? Because you're adding an ML component to it, you're doing this data transfer. And what we see is that really it gives you about a 10 to 20% performance hit when you're running these ML predictions on the GPU in the database. So depending on your application, depending on the accuracy that increase, this may or may not be beneficial to you. This may not be a trade-off, but in general, right, we do see marked improvement in a lot of these metrics that we care about when we're looking at the fidelity of the simulation. Another example of things, we wrote a paper recently where we integrated OpenFOAM, which is a CFD solver, and created a SmartSim integration with it. And we had basically a bunch of different, really simple, but hopefully explanatory kind of ways of how you might want to do AI integrations with your simulation itself. So it's both like a paper about like how do you couple this, but then like what can you do after you couple this? And so a couple of the in the loop kind of applications for that, one that might be of interest to the community is that we did demonstrate this online training and online inference, where instead of just running inference like in the other one, we were actually training a model on the fly as well, at every time step. And so essentially what was happening is that they wanted a way to solve the problem of how do you move the mesh of a simulation based on the boundary displacement. So the example that we used was this kind of just very simple airfoil here on the right-hand side. The airfoil has a prescribed motion and you want the mesh to move with it. And so what we did, we trained a model on the boundary displacements, and then the prediction was then done on all the interior parts of the mesh. And so if you look at this animation, you see this happening. Red is where the ML model is much more improved in terms of the quality of the mesh over the traditional implementation of a plot-chain-based thing that was originally in OpenFOAM to do this mesh motion problem. So in general, we see a better improvement of the quality of the mesh. And you can extend this to more complicated things that's being done currently. The other part that we also showed was that you can actually implement a streaming principal component analysis really easily when you have the ability to extract information at the time step level, right? So that's what's being shown down here. We implemented distributed partitioned SVD to do the principal component analysis. And what you end up getting at the end of the day is just the principal components themselves. You don't have to do that analysis after the fact. You can do it while the simulation is running. And then lastly, for the in-the-loop things, we are figuring out new ways of training surrogate models. So one of the things that we know is that traditional offline surrogate modeling relies on just a corpus of data just sitting on a file system. And that data has already been decimated in some way, right? It's already been reduced either in time and or space, otherwise you're going to be saving hundreds of terabytes, if not petabytes worth of data. And so what we showed here is that you can actually do something where you extract the simulation data at the time step, intelligently sample it, so you're only training on interesting parts of the solution space, and then doing this in a streaming fashion, right? So you don't just store that data, you're just constantly getting new data, constantly training and tuning your model based on incoming data that's generated by the simulation. And because you can do this at the time step level, you get all those high frequency and high wave number processes that the model is then able to learn on. Okay, and then I'm just going to run through this real quick. So now we're going to talk about ML around the loop. So this is where you do inference or training after the simulation. And the first one that we'll show is that this is a now classic paper about how you basically use some things that you might want to call generative AI, but how you use AI to solve the problem of protein folding. Right. So in this particular case, we're going to say, like, it's the protein folding problem. So you want to figure out, like, what are the configurations of a protein that lead to the smallest energy state, the lowest energy state, right? And so with all the degrees of freedom that are in any simple protein, this has a large search space. And so one of the questions, how do you explore the search space efficiently? And so here, what we end up doing is that we recreated this now classic paper in SmartSim, but we did everything so that everything was online and did not use this database to kind of store intermediate state. And so what does this workflow look like? Okay, so we start an ensemble of MD simulations, molecular dynamic simulations. And we wait for the new checkpoints, either from checkpoints that were from previous simulations or just an initial set of them. So each simulation then discovers and uploads their configurations independently, right? So this is the kind of final state. And then the final states are used to train a generative model of some variety, essentially saying, like, okay, based on what the final configuration was, like, what is a new set of configurations that might lead to a lower energy state? The generative model is then fed to an outlier detection application. So it says, okay, well, all these are really similar, except for this one. This one is a novel thing that we haven't seen before. So let's do that. Let's use that and then try that best one as the starting configuration for the next set of iterations, right? And so then this continually loops. Everything here is done asynchronously. So you're not necessarily waiting for each and every individual molecular dynamic simulation to complete. You're not waiting for all the models to train. Everything is kind of done in a loop until you get to a low energy state protein configuration, right? So this is kind of a fire and forget, right? You're trying to take advantage of as much asynchronicity in the computation as possible. You're doing things where you're wrapping these AI techniques around the simulation so that you're to achieve a final goal. And then another paper that recently came out that used SmartSim to do this was the question of how do you control fluid flow. And so in this particular case, they wanted to say there's a turbulent rising bubble, and they wanted to reduce the recirculation length by actuating something upstream of the flow. So here's an animation of that, right? So there's the bubble that's kind of in the first third of the flow. And essentially what's happening here is that you're giving a this reinforcement learning model some observation of the flow upstream and downstream of this bubble, right? And you're saying, okay, like here's the state of the world that you care about. And then what it can do is that there are some actuators upwind of the bubble that it can actually like move, right? So these are just kind of like flaps that go back and forth, and you can give it an angle or a position that you want it to reach. And so the question is, what is the optimal set of things based on the observed state of the system that and like how would you modify those flaps to reduce the recirculation length? And so what's being shown on the bottom here is that there was a previous paper that showed that there is kind of a technique to do this, and what's being plotted on the y-axis is the recirculation length of the bubble. On the x-axis is the time as it evolves, as this turbulent state evolves. And then the left panel is this previous optimal one. The middle panel is a sinusoidal control where you just specify some ideal frequency. And on the right-hand side is this reinforcement learning solution here. And so the big things that you can see is that the simple sinusoidal control has large excursions, which is not very desirable. It represents a very unstable system. The machine learning one does not have that high frequency variability. It looks more like the optimal control, but it does achieve actually a smaller recirculation length than the original one. So that's a pretty, so that's one of the things that we see a lot of people interested in. You can cast this in a data assimilation framework. You can cast this kind of in a control system framework where you want to be able to control some behavior of the system by using something like reinforcement learning. Okay, and just to make sure we have time for everybody else, just want to really skip through some general conclusions and findings that we had. So I hope I've convinced you that there's a lot of interest or that there's some interesting things that you can do when you have a workflow that can be kind of loosely coupled data-driven workflow where AI can be a component of it. And that they go beyond the traditional ways of describing computational, right? Things like a directed acyclic graph. This is not just something that can be described by that. There's loops, there's conditionals that you might need to do. And the other thing is that, ML is actually a pretty relatively easy thing for scientists to pick up. A lot of it relies on the statistics that all of us are familiar with. It's not a very large extension from doing statistical modeling in general. It's just at a different scale. And, one of the nice things is that because there's been a lot of interest in this, the tools are actually relatively easy to learn. There's a lot of tutorials out there. And then the third point is that AI and simulation really, it's a burgeoning kind of field. So almost anything that you do in the field is a new opportunity for scientific discovery. So even some of these really small steps in toy problems, are really important foundational pieces of information that we have to guide the entirety of the domain to figure out okay, is this a useful way to go forward? Is this not? What are the optimal techniques? What are the best practices? So it's really one of these really interesting and vibrant fields where we have a lot of discussion. We see a lot of people who are interested. We get a lot of people who are excited about the possibilities of applying these to larger things. And so really, it's a very exciting part of the research field to be in. And then lastly, if you were ever inspired by anything that we said here and you want to follow up, please reach out to us. We're very open to collaboration. That's what most of my job is. And we work with a large set of people to kind of figure out, how to explore these things and make it easier for you. And so with that, I'll share these slides later, but there's many ways you can interact with us just kind of passively. You can follow us on GitHub, our various repositories. We have a Slack space that you can also join as well. We'll drop the link in the chat. And and that's basically it for my portion of the talk. So I don't know if we want to take questions now or just pass it off to the presenters and do one large round, but thanks for listening.
Yeah, there was a question in the chat that I'll answer. So maybe we should just carry on so that we can get to the end and then we'll have a general question session after.
Sure.
Yeah. Okay, so I can take over now.
Yeah.
Okay, great. So yeah, I'm going to talk a little bit about using SmartSim on ARCHER2. So I'm a complete novice at using SmartSim. So this is kind of my first experience on trying to sort of build it and get it running and trying to test it and run an actual kind of sample application on ARCHER2. So yeah, as mentioned, this is my first experience with using SmartSim, and yeah, first time using it on ARCHER2. So I had a few things that I wanted to look at. So how can we install SmartSim on ARCHER2? How should we run it? How can we make use of the batch system on ARCHER2? And then looking at the resources, use of resources for this database and the HPC application. So how can we, smartly run these on ARCHER2? And then looking at running SmartSim, so I've already mentioned this database does all the machine learning part. Can we run this on the GPU because that kind of makes sense? And then the applications typically using CPU only. And then finally, yeah, what I looked at was running a sample application that uses SmartSim on ARCHER2. So first of all, looking at installing SmartSim. So I had to install the SmartSim and SmartRedis Python packages. So these can be done within a Python environment. So I actually did this based on our own ARCHER2 PyTorch installation, which is available as a module. So you can load this PyTorch module. There's a CPU version and a GPU version as well. And then setting up these Python environment variables. So yeah, pyenv-root and the site packages. And then once you've got this, you can build your own environment and activate it. And then your PyTorch is available. And then you can also go and pip install these SmartSim and SmartRedis from the GitHub repos. So for SmartRedis, you also have to install the C++ and Fortran libraries because these need to be, they are used in your HPC application for accessing the SmartRedis client. So this was quite easy, just cloning the repo and then doing, a make. And then finally, you have to build Redsi, and the machine learning backends. So this is done with this smart build command. This is part of SmartSim, so this is only available after installing the SmartSim Python package. But this command, you can specify whether you want to build for CPU or GPU, and then you can pass your own PyTorch installation using this torchdir and yes, applying the CMake prefix path. So this is what I did here, so that we can use our own, the PyTorch that's available on ARCHER2. So first thing I did was run a kind of simple SmartSim Hello World batch example. So this is quite similar to the example Andrew showed earlier. So this is just a simple Python script that launches SmartSim and does a kind of very simple hello world. So yeah, this imports the experiment module from SmartSim, and then the first thing you're doing is creating these run settings. So you pass your executable, any arguments, and then your run command, which launches it, which is here is srun. So this is just a simple echo command. But in reality, if you were running an application, you'd be passing your application binary here. And then these other run settings you can set, such as the number of nodes and the number of tasks, are quite sort of straightforward. And then batch settings. So here you can create a set of batch settings for launching the job. So here you can see the nodes and the time, kind of normal things. For ARCHER2, we can then specify the queue as standard, which is the partition in this case, we're familiar with, your account. And then the QoS has to be passed as through this batch args argument because it doesn't have its own kind of standard one. But then from this, you can then run the model, and then this will launch on the back end and run hello. So launch a batch job. So yeah, we can also create a database or the orchestrator from the experiment. So this is your in-memory database that uses Redis and Redis AI, and then provides a distributed database to access the machine learning backends. So this stores all the tensors and the machine learning models and scripts. And then it can also execute these machine learning models, which are written in Python on either CPU or GPU. So this little Python script here creates the database. So this looks kind of similar to before. You specify the number of nodes, you give a default port for it to use, and then specify whether it's running on, whether it's to be run on as the batch or not. At the time, the interface is a different one. So this is your network interface. So for ARCHER2, this is HSN0, and then your account and yeah, partitions, kind of similar as before. And then if you run this, it will print the hosts that the orchestrator is being launched on. And again, yes, we'll submit a batch job that will run on the nodes. So, I decided to look at this MOM6 application. So this is the modular modular ocean model from that was mentioned previously. This uses PyTorch and predicts the eddy kinetic energy. So this needs to be built, including the smart Redis libraries. So to build this application and then pass the paths to your smart Redis libraries that you've installed previously. And then it includes this driver script. So this launches SmartSim, and then yeah, you supply your machine learning model you're using and your the path to your binary for MOM6. So I had to make a few modifications to this driver script to get it to work on ARCHER2. So this involved, add-ins, kind of some things we've seen before. So the account, the partition, and the QoS. And then I also need to add this preamble setting in order to give the path to the smart Redis libraries at runtime, so it can find those. So this is, this part here is for the MOM6 model. And then this part here is the settings had to change for the database. So adding in these parts to allow it to use the ARCHER2 batch system, such as your partition, specifying the interface here, and the and also add in this preamble to load the PyTorch module so that it can access PyTorch. So running this MOM6 model on ARCHER2, so this then goes and launches two jobs from that driver script. One of them does the MOM6 application, and one of them does this database. So the MOM6 application is run on the CPUs, and then you have your database, which can be run either on the CPUs or on the GPUs, depending on which PyTorch you specify. So I was able to get this working on both. And it runs two separate instances. And this is the job script that is generated by SmartSim for the database. So this has taken all these settings that you supply in the driver script and then use them as these sbatch commands. And then you've also got the PyTorch module that was specified before. And then the srun command, so this launches the database. It uses your Python environment and then launches the Redis server. And you've got the Redis configuration file, and then it loads the Redis AI libraries as well. You can also see it specifies the port number and the network interface name that's been pulled through as well. So I've modified this a little bit from what it actually looked like to make it a bit easier to read, but yeah, it's specifies all these different things that it generates himself. And then this is the MOM6 job script, also generated by SmartSim. Again, it's got all the batch settings pulled from the driver script. You've also set the library path that was also set in the driver script as preamble. And then here the srun launches the MOM6 application. So it specifies the tasks used. And then these environment variables here, so you have the SmartSim database address, so it specifies the address and the database of your address and port of your Redis database. And then these SS key variables, so these are the prefixes that get attached to the tensors and data sets, which helps them when they're being transferred between the database and the client. Running out of time a little bit. Okay, so yeah, this is what actually happens when you launch this driver script. You can see it prints out what's happening, all your different settings, and then it queues 2 separate jobs, one for your orchestrator, one for your application. And you'll see that it polls and checks sort of how they're running and manages the execution of these different components. So one thing to note is that these jobs queue separately, so you can find that the orchestrator will start running, but then there's not enough resources to run the application, and then you're kind of waiting, just a bit of a downside. And then, so what I also looked at, oh, I just made a mess of my slide, is using het jobs to do this rather than getting the driver script to launch the batch jobs. So in this case, you've got a het job for the CPU part running the application, and then a GPU het job for the database. And then you turn off the batch launch from the driver script because you don't want it launching it itself. And then you can run this. And then if you add in the relevant het groups as arguments to your srun, you can tell it to run the orchestrator on the GPU part and then the application on the CPU het job. So quick recap. So we demonstrated how to run and build SmartSim examples on ARCHER2 with no prior experience. I found kind of the most of it was involved in building the MOM6 application and then also kind of working out how to configure this driver script so that it would run on ARCHER2. And I was also able to run this database on the CPUs and on the GPU development platform, admittedly only kind of one GPU. But yeah. So shall I hand over to Andrew?
Yeah. So Andrew, don't rush. I mean, there's no rush to finish. We can carry on past the hour.
Okay, great. Hi, can you hear me okay?
Yes.
Great. Yeah, so I'm going to talk a bit about some recent kind of experiences that we have, recent ongoing experience we have with using SmartSim for our application, which is looking at kind of dynamic wake steering in wind farms, and kind of the experience we had with coupling the machine learning part of that with our fluid solver, which is XCompact3D. So first, just a little bit of background for the problem that we're looking at. When we have big wind farms like this, you can see we have wind turbines, and these wind turbines generate a wake behind them. And in big, large wind farms with many wind turbines, lots of these wind turbines then operate in the wake conditions of upstream turbines, and this reduces their power output because we have lower wind speeds. And so one thing we can do to kind of mitigate this is control the yaw of the wind turbines. So if we have a wind turbine with the wind coming from the left here, we can just change the angle of the wind turbine to move the wake position around behind the wind turbine. And so we can use a wind farm simulator with XCompact3D to kind of simulate this effect. So here's some results of that. You can see here we have 4 wind turbines. The wind turbines on the left is unyawed, and the one on the right is yawed, and that's deflecting the weight behind it to the slide slightly, and that then exposes this downstream wind turbine to more airflow, so you can get higher power output. And if you look at the power output from this, you can see if we kind of steer at the correct angle, we get an improved power output. And this is great in a kind of static sense. We can find a yaw angle that kind of improves the power output of our wind farm. However, there are lots of dynamic effects going on in the wind farm. The wind speed is constantly changing, the angle, the kind of direction of the wind is changing, and then we also have these kind of dynamic effects of the kind of wake. So the kind of interaction between the turbulence of the atmospheric boundary layer and the wake cause it to kind of move around. So this is the problem that we want to control, and that you can see it here, kind of with it comparing the instantaneous and the mean flow, and how it kind of deviates from the mean, and it is instantaneous. So this is the kind of what we want to control, and kind of improve using kind of machine learning. And so we tend to kind of reinforcement learning to try and find a control mechanism for this kind of dynamic problem. So the idea behind reinforcement learning is we have an agent and we have an environment, and these two interact, and they interact through actions, states, and rewards. And so the agent will output an action which will be fed into our environment, and our environment will kind of output then the kind of state of the environment, and also a reward function based on that action. And this will be an input into our agent, which will decide the next action. So when we apply this to our wind farm setup, our action is a kind of change in the different yaw angles of the turbines in our wind farm. Our environment is a large eddy simulation of our wind farm, with the kind of effects of the wakes. And then the output will be from that environment, the reward will be the kind of power output of our wind farm, and the state will be some kind of flow measurements that we can capture from that. And so we started off by trying to kind of implement this reinforcement learning loop using just a file-based system. So we had XCompact written in Fortran for our large eddy simulation of our wind farm, and we had our kind of reinforcement learning algorithm written in Python and PyTorch, and we just output the kind of actions. So from our kind of LES, we stored onto file the kind of state and the reward, and then we read these into our RL algorithm at each kind of step of our RL, and then we would pass that through and obtain an action, which would store on our in our files again, and read that into our LES. And this kind of worked okay for a bit. We could train it for a kind of short amount of time. However, we had a number of issues. The I/O was kind of slowing down the interaction as we were trying to write to file. As we kind of increased the number of observations we were making in the flow, this led to quite large files that we were having, or relatively large files that we were having to write to very often. And then we were also having to stop and start these simulations, which was very costly. So this kind of was a problem that we had, and then that was only going to grow as we tried to increase the size of the wind farm and increase the kind of number of environments that we were training in. So one thing we wanted to do is use these multiple environments. So rather than kind of just training with one environment, we used lots of them at the same time, and that was just kind of multiplying the problem we had. So this is where we turned to SmartSim and used this to kind of improve our coupling between the environment and the RL algorithm. And so we did this kind of using the same method we had before, except now we replaced our file database with a in-memory SmartRedis database. And this then again contains our actions, our states and rewards. It now also contains some flags to pause our simulations or our algorithm, depending on which one was working. And again, we then pass these back and forth, the states and actions between now the SmartRedis database and our simulation and our algorithm. And so just to kind of a kind of overview of the kind of modifications we had to make. First of all, to our the XCompact, we had to replace the subroutine that was doing our I/O, and we replaced that with a subroutine that uses the SmartRedis client. And so here you can see we kind of put the tensor onto this SmartRedis database, and in this case the turbine powers, but also the whether we kind of want the simulation or the RL to continue. And then on the Python side, we have a communication. Again, we use the Python API to SmartRedis API to then collect that tensor into our RL algorithm, and then we also kind of reset those flags to allow our simulation to pause. So then we have these kind of small modifications to both sides that allow us to do this coupling through SmartRedis. Yeah. So then we also used the SmartSim to kind of orchestrate this. So we set up, on the left, we set up the experiment and set up the kind of RL code, and then a series of different environments as well. So we go through N environments to kind of launch then multiple simulations at the same time. And then we start everything with the SmartSim kind of orchestrator here. And then we monitor them all, and if anything stops, we stop everything else. So we're not wasting anything if anything goes wrong. And you can see the kind of the output we get from this at the end is we have our PPO reinforcement learning algorithm, and then 32 wind farm environments all running at the same time, and an orchestrator that kind of allows us to use the SmartRedis database to interact between those environments and the RL algorithm. So we did this with a setup with 10 wind turbines in a row. We did this with, again, as I said, 32 parallel environments, each environment running on a core on a single node on ARCHER2, so 128 cores. And then we did 50 simulation time steps per reinforcement learning step, where we exchanged the actions and the states and reward. And then we kind of, so that's where we do the inference every 50 steps, and then we kind of collect these up and train every 500, roughly every 500 frames. And that then has allowed us to kind of extend our training into to collect kind of up to like about 1 million frames of the reinforcement learning, which is kind of ballpark how long we need to train these kind of algorithms. So just a note on the kind of speed. Previously, it was taking about 15 minutes to collect kind of these 512 frames, and now we're getting it down to about 50 seconds to collect 500 frames. And so this is a dramatic speed up that this has allowed us to then train for a much longer time and kind of improve the RL output. And so you can see kind of some of our initial results. At the top we have the yaw angles of all the turbines, and the bottom the power output of the wind farm. And if we kind of look at later on in the training, you can see that the neural network has learned how to control the turbines with this kind of sinusoidal pattern. And if we look kind of closer and kind of look at the frequency here, you can see that the kind of turbines at the back of the wind farm are then learning to pick up a particular frequency for the control that is then improving the power output over our baseline case. So we're kind of getting an improvement in the per output by this kind of dynamic strategy of following the weight meandering. Yeah, so just to summarize, we're using reinforcement learning to test or explore dynamic and active control in these wind farms. We're including kind of this physics from the higher fidelity large eddy simulations running on ARCHER as the environment for our reinforcement learning, and SmartSim has kind of allowed us to efficiently couple that environment and the reinforcement learning on HPC. Thanks.
Yeah, thanks a lot. Thanks to everybody. So are there any questions? I saw there were some questions in the chat about, data volumes and whether that would be an issue or not. So I don't know if they were answered, but I don't know if anyone wants to, if they were fully answered. Yes. So I had a question about the wake steering. So are there any engineering constraints in how much you can steer a turbine or any dangerous situations that it can get into based on the turbulence or the wind speeds that you have to be aware of, or there are other controls on top of what the machine learning model might want to do? Does that make sense?
Yeah, so there are quite a number of constraints you have based on the kind of speed of your actuation and the range of your angles that you might want to look at, and so we've kind of included some of those, maybe not all of them, but we've kind of tried to include as many of those as possible into our algorithm, so it's constrained to this kind of specific yaw angles and constrained to kind of speed of actuation of the yaw angle that is kind of representative of the kind of constraints you have in a real setup.
So I'll hand back to you, Juan. I think there are no more questions.
Yeah, if there are no, I see that there were some in the chat, but they were answered. Thanks everyone for joining. Yeah, have a nice rest of the day. Well, also thanks to the speakers. Has been a interesting webinar. Bye for now.
Bye.